Hi guys, welcome back to In Case of Econ Struggles. Today I'm going to keep talking about econometrics. In particular, I'm going to keep talking about the OLS estimator beta hat. I'm going to talk about why if we have those 5 Gauss-Markov assumptions that I've talked about in a previous video, then our OLS estimator is blue, which means it's our best linear unbiased estimator. I'm going to talk in this video about what it means to be linear, what it means to be unbiased, and what we mean by best. So timestamps are below if you would like to jump around, but let's go ahead and get right into it. Now when I say something like OLS is our best linear unbiased estimator, the reason why I'm saying that is because we've got all possible estimators, and of those estimators, a subset are going to be linear estimators. Again, I'll talk about what linear means in a second here. We've got a subset of estimators that are linear estimators, and a further subset of those linear estimators are unbiased. Talked a little bit about what unbiased meant in a previous video. And of those unbiased linear estimators, there's one set of estimators or a couple estimators that could be best. By best, we mean have the smallest variance. So what we're trying to show in this video is that if we have the 5 Gauss-Markov assumptions, then our OLS estimate is our best or smallest variance linear unbiased estimator. And so what we need to do in order to prove that, and I'm going to prove that in this video, I'm going to go through step by step, and first I'm going to prove that our beta hat is linear, then I'm going to prove that our beta hat is unbiased, and then I'm going to prove that of our linear estimators, our beta hat has the smallest variance. And so really what I should have on this slide is these should all be beta hats, because I'm focusing on the properties of the estimator beta hat, not beta, which is going to be the true value that I don't necessarily know. Just a couple things before we get started here. First, I need to assume that all 5 Gauss-Markov assumptions hold. I've talked about the 5 Gauss-Markov assumptions in a previous video. If you're unfamiliar, it's going to pop up in the top right corner right about now for you to check out either after this video or before you keep watching. I'll point out as I go through the proof when I invoke some of these Gauss-Markov assumptions, exactly which assumption I'm invoking. Now, as I go through, I really want to use matrix notation for most of my proofs. Matrix notation, it's easier, it's more flexible. You can use it for simple or multiple regressions. It's also more likely what you're going to see in econometrics classes, especially as you get further into the semester or further into econometrics. So it's just helpful if you start seeing it now. I'm going to differentiate my notation where if I use I's, that's going to mean that I'm going to use observational level, so not matrices. And then if I put just big letters without any subscripts, that's going to denote that those things are matrices. So for instance, this is the matrix X. This is the matrix of all my regressors. X sub I, this is going to be a regressor value for a particular variable for a particular observation I. Okay, so just to start getting into it, just to get a little warm up, I'm going to show that the OLS estimate is linear. And basically we want to show that our estimator beta hat is just some linear combination of observations where I basically have these observations y1, y2, y3, and yn. And basically what I can do is that I can assign specific weights to each of these observations. And if I take the weighted sum of those observations, I'm going to get to beta hat. And we know from our definition of beta hat, not talking about matrices, talking about in terms of just at the observational level, if I think about a simple regression, this is what my beta hat is. And I've talked about that in a previous video. I'm just going to take yi minus y bar, and I'm going to split that up. And then what I'm going to do is I'm going to further split this sum up like this. So this is going to be the sum from I equals 1 to n of xi minus the sum from I equals 1 to x bar. The same thing on the right-hand side of this minus sign. And one thing I know is that I know that this sample average is always the same for every observation because it's just the sample of x. So the sum from I equals 1 to x bar is just n times x bar. And then I also know that what's happening is 1 over n times I equals 1 to n of xi is x bar. So what I can do is I can turn this sum right here, the sum of xi minus 1 to n of x bar, into this sum right here. And that's going to be equal to 0, and so I can just zero that out. So now what I'm going to do is I'm only going to zero this out on the right-hand side because this is y bar. That doesn't change either. This yi doesn't go to 0 because I want to keep that in here, because ultimately what I want to do is I want to rewrite beta hat as the sum of something times yi, where this something is going to be the weights on each observation. So I want to keep this yi in here. And if I just zero it out, then I get 0 on the top, and then it doesn't really make any sense because obviously it's not a sum of 0 times yi, it's a sum of some weight times yi. So I'm only going to zero out the part to the right-hand side of this minus sign, and then I'm going to get a sum that looks like this. Well, I'm just going to say that alpha I is going to be this whole mess right here. And then I can say that beta hat is the sum from I equals 1 to n of alpha I times yi And so now I've shown that it's a linear estimator because I can write it as a weighted sum of my yi's. And so what you can see is that was sort of cumbersome to go through, and now I'm just going to show the same thing with matrix notation just so you again get the hang of it. And so I have beta hat, where beta hat is xt x minus 1 xty. And so what I know is that xty is basically this term right here, or the variance of x. X prime y is just the covariance of x and y. And so now what I have is I basically have xi minus x times yi divided by the sum from xi minus x bar squared. And now I can do the exact same math that I did above, and I'm going to get to the same point where now beta hat is a linear estimator of y, where the xt x minus 1 xt part, that's the weights on my y's. And so that's what I'm using basically as those weights. So now I know that my OLS estimate is linear. Let's talk about how we know it's unbiased. And again, now I'm going to switch fully into matrix notation. Basically, what we want to show is that our expected value of our estimator beta hat is equal to the true beta, even if I don't know what the true beta is. So now I'm just going to start from my estimator, which is, again, xt x minus 1 xty. And I know that y, the true y, is just x times beta plus epsilon. And so all I'm going to do is sub that in for y. And now what I'm going to have is I'm going to have beta hat. This term is going to be xt x minus 1 times xtx from this part right here. Well, I know that this inverse times this non-inverse is just the identity matrix I. And then I have xt x minus 1 xte, so this part right here. Now I know that if I cancel this and this becomes an I, this is going to become the true beta. Now I have this expectation, if I put the expectation on beta hat. The expectation of beta hat is beta plus the expected value of this guy right here. But because of our Gauss-Markov assumption, we assumed that there's no correlation between our error term and any regressor. And so the expectation of xt times epsilon is 0 by our Gauss-Markov assumption, which means that our expected value of beta hat is our true beta, which means we're unbiased. And finally, the hardest thing we're going to do today is show that our OLS estimate has the smallest variance of any linear unbiased estimator. And again, I'm going to use matrix notation. So some things that we know from before is we know that the variance of beta hat is just basically beta hat minus beta times beta hat minus beta. And so that's just going to be this guy right here, or basically the expectation of beta hat minus beta quantity squared. And I know that the variance of my error term is just the identity matrix times sigma squared epsilon, or sometimes you'll just see it as sigma squared, or which is just equal to the expectation of the error term squared. We also know from unbiasedness that our beta hat is just equal to beta plus xt x minus 1 xt epsilon, where before we canceled this out to 0, but now we can't do that because we're not yet taking an expectation. So because we haven't taken the expectation, this is what we have so far. And so if beta hat is beta plus this stuff, that means that beta hat minus beta is just going to be this term to the right here. And so that's what we're going to use. So now we're just going to use the definition of variance. And so I have this term right here, which is beta hat minus beta transpose. This is beta hat minus beta. I'm just going to distribute this transpose. And now what I'm going to get is I'm going to get xt x minus 1. This is an x, this is an xt. They're going to cancel again. You have an et and an e. That's just sigma squared e times I. And I have this term right here, which is sigma squared epsilon xt x minus 1. And I've shown you before that this is the variance of beta hat. I've talked about it in my video on standard errors. If you want to check that out, it's going to pop up in the top right corner right about now. But regardless, now we know, or now we remember what the variance of beta hat is. So now what I need to do is I need to show that this variance right here is less than or equal to the variance of any other linear unbiased estimator that I can cook up. And so now what I'm going to do is I'm just going to cook up some other linear unbiased estimator. And I'm going to say that it's going to be c times y, which is basically going to be, I'm going to take beta hat and I'm going to add some non-negative matrix D to that estimate. And so that's how I'm going to get c. And so beta hat is going to be c times y. And that's what I'm going to have as my estimator. That's going to be beta tilde. So now I'm just going to figure out the variance of beta tilde. It's going to look very similar to what I did for beta hat. And now one thing that I have to do is when I get to this step right here, where again all I've done is I've started with this is my beta tilde minus beta, beta tilde minus beta. I'm going to plug in that y equals x beta plus epsilon. That's going to give me these terms right in here. And now what I'm going to say is I'm going to say that my CX is equal to my identity matrix. Once I do that, I'm going to have CE times CE transpose, which is going to look something like this. And I know that E transpose E is just sigma squared times I. So now my variance of beta tilde is equal to this guy right here. Now what I'm going to do is I'm just going to invoke the fact that C is this D matrix plus my beta hat. And so now what I'll do is I'll just sort of, again, plug that back in. I'll do the transpose, I'll distribute that transpose, and I'll get D transpose D. I'm again going to get XTX minus 1 times XT times X. And so that's going to cancel out and become an I just like that. I'm going to distribute the sigma squared epsilon. And when I distribute that sigma squared epsilon to the second term, well, I know this. I've seen this before. This is just the variance of beta hat. So I'm going to write this as beta hat. And this is going to be the term that's left over is sigma squared epsilon times D transpose D. And this matrix D has to be greater than or equal to 0. It can't be less than 0. If this D is less than 0, then we're going to have a bias estimator, so this D has to be greater than or equal to 0. What we have now is our variance of beta tilde is equal to the variance of beta hat plus some number that's greater than or equal to 0, which means that beta hat has to have the smaller variance. It's got to be at least as small as the variance of beta tilde, if not smaller. So now we proved that our OLS estimate has the smallest variance, which means it's our best estimator. We know it's linear, so it's our best linear estimator. We also know it's unbiased, so it's our best linear unbiased estimator. So again, hopefully this just makes it make a little more sense why our OLS coefficient is blue. If you still got questions, if you want me to clarify something, feel free to put that in the comment section below. But if this video or these videos in general helping you out, please like and subscribe, and we'll see you next time for another case of econ struggles.